Hello friends, welcome to my channel. Let's have a look at problem 2444, count subarrays with fixed bounds. In this video, we're going to share a solution based on sliding window, more precisely three-pointer sliding window. First, I'll read through the statement of the problem to digest the requirements, and then we do a detailed analysis, and finally we share and explain the codes. First, the statement. We are given an integer array nums and two integers min key and max key. A fixed bound subarray of nums is a subarray that satisfies the following conditions. First, the minimum value in the subarray is equal to min key, and the maximum value in the subarray is equal to max key. So we are required to return the number of fixed bound subarrays. So in other words, we want to count the number of fixed bound subarrays, and this fixed bound subarray has its min value equals to the min key given, and the max value equals the max key given, right? So here are two examples. Let's first look at example 2. So example 2 is special in the sense that the min key and max key are the same, and all the elements in the list are also the same, and they equal to the min key or max key. So in this case, we just need to count the number of different subarrays, right? So here the output is 10. The reason is that we have 4 length 1 subarray, 3 length 2, and 2 length 3, and 1 length 4. So we have 4 plus 3 plus 2 plus 1, that is 10. This is example 2. And for example 1, so the min is 1 and the max is 5. So in this problem, the output is 2. So the corresponding two subarrays are 135, right, and 1352. So notice that in this problem, the number 7 is out of bound, right? It actually split the list into 2, right? 1, 3, 5, 2, and 5. However, the single element 5 does not form a valid fixed bound subarray in the problem sense. The reason is that this single element array or list does not include the min key. So with that said, let's look at the constraints of this problem. First, the length of this list is bounded below by 2. In other words, has at least 2 elements, and bounded above by 10 to the power 5. The 10 to the power 5 actually defines the problem size upper bound. The second constraint is on the range of elements. For example, nums I, min key, and max key. They are all in between 1 and 10 to the power 6. So with that said, we are ready to do the analysis. So here the treatment will be based on sliding window. So we can use 3 pointers. So here the idea is actually very straightforward. So what we want to do is that for each index I, we want to find the number of fixed bound subarrays ending there, right? So then we sum the contributions at all the indices, then we get the return. So notice that it's possible that at certain indices, there's no valid fixed bound subarray ending there, but that's fine, right? So let's look at an example to fix the idea. So this example is cooked up to show the generic case. So in this example, the length of the nums is 11, and the min key is 1, and the max key is 5. So here, let me first point out that at the index 0, the index 10, the element is out of bound, right? So we have none and none. It's out of bound of 1 and 5, right? So here, let's first make some simple observations to gain intuition. So at indices 0, 1 up to 5, so this here, right? So we notice that there are no max key to their left, right? So the number of fixed bound subarrays ending at these indices are all zeros. So their contribution to the final result is in 0. So now let's look at the ending index 6. So this is 6, right? So this one, so this is a red pointer, right? So then if we examine to the left, so we have 1 at index 4. So if we start from index 4 and ending, then so we can get all the start indices, such that if we start at start indices and ending at index 6, so we have valid fixed bound subarray. For example, if we start from index 4, we get 1, 2, 5, right? If we start from index 3, we get 1, 1, 2, 5, and then we can include 3 at index 2 and 3 at index 1. Both are okay. So in this case, the start index can be 1, 2, 3, 4. So there are 4 valid ones. So this 4 actually equals 4 minus 0. So this where 4 is the mean of rightmost indices of mean key, that is 1, and max key 5 for subarrays ending at index 6, right? And 0 is the nearest out-of-bound number index. So here this is none, right? So the difference gives us the number of distinct starting indices. This also equal to the number of valid fixed bound subarray ending at index 6. So similarly for ending indices at 7, 8, 9. So we have the rightmost indices for min key and max key is 4, right? So the start or the nearest outbound index is 0. So we get for each these 3 indices 7, 8, 9. So all the starts can be 1, 2, 3, 4. So each contributes to 4 valid fixed bound subarrays. If we look at the index 10, so index 10 is not a valid number in bound. So in other words, it's not in between 1 and 5. So there is no valid fixed bound subarray ending there. So overall, the return is 4 times 4. The first 4 is the 4 indices, for example, 6, 7, 8, 9. So the second 4 is the 4 possibilities for starting indices corresponding to each of the 4 indices. So we get 16. So this actually demonstrates the idea. So here I would like to make a remark before we write the code. So once we digest the above idea, actually we could also do the coding in a reverse order. So we iterate from end to front, and for each indices, we find the number of fixed bound subarrays starting there, right? And then summing the contributions at all indices, we also get the return. So our plan is the following. First, we'll write a code, so using iteration from the front to the end, and then we try another format, so writing the code or iterate through from the end to the front. So first, let's look at version 1. So we start, we iterate from beginning to the end, right? So this actually is more sort of strict. So first, I'm going to initialize a result variable. So this will counting the valid fixed bound subarrays. So here I'm going to initialize 3 more variables corresponding to the 3 pointers. Let's see. So corresponding to 2 of the pointers. So the red pointer will be the iteration indices. So first, the outer index. So, and the second is the M index, and the third one is the capital M index. So it's initialized to be -1. So here I changed the min and max to be little m and capital M for convenience. So this outer index will record the nearest outer bound indices, and the 2 variable m little m index and the capital M index will give us the rightmost indices for min key and max key. So meanwhile, I want to introduce another 2 variable mSym and capital mSym. So we want to check and make sure, so for a certain piece, both the min and max, in other words, the little m and the capital M are same. So originally, so we have false and false. So this finishes the preparation. So let's call it preparation. So next things will be straightforward. So we are going to do iterate from front to end. So for this, we are going to do for I, y in enumerate nums. So here first, if y is less than little m or y is larger than capital M. So this case, so actually this element y is out of bound, then we can update the outer index. So outer index to be I, right? But in this case, ending at this index I, so we still haven't seen little m and capital M simultaneous on both. So we want to set m thin still is false, and capital M thin is false. In other words, once we met such element, we need to start over again to start a new beginning, right? So this is the one case. Another case is if y equals little m, right? So in this case, so we are going to update the little m index to be I. And in this case, we have thin the little m, so we set m thin to be true, right? So another case is if y equals capital M. So in this case, we thin the capital M, so we set or update m thin to be true. And then what we're also I need to actually update the indices, right? So let's do it first to make it parallel to the above if clause. So this is this finishes the examination for elements and for updates for the variables. And then what we are going to do is that if m thin and m thin are both true, so in this case, in other words, ending at current indices I, so we could see both little m and capital M, and then we are going to increment the result. So the result increment is nothing but the mean of this m indices and capital indices, then minus the outer index. So here, this minimum of min IDX and max IDX corresponds to here, right? For example, if we look at index 6, so the rightmost 5 is here, and the rightmost 1 is here. So this is the minimum of the rightmost 5 and the most rightmost 1, that is 4, right? So this is the break number. So then 4 minus 0 gives us this 4 possibilities. So similarly there, right? So that also explains why we initialize outer index to be -1 if there are no elements out of bound at the very beginning, right? So this is the process. So next, so we just need to do the return. So we return the result state. So this actually forms a format of solution. So now let's do a generic case check. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. So with that said, actually, this is a version that we iterate from beginning to end. So once we add that the logic, so we can actually do this with a lot of freedom. So we can actually also iterate from end to front. So let me change this version to be v1. And now let's look at the second version. So for the second version, we're going to iterate from end to front. So first, we do some preparation. The result variable does not change, and the outer indices and m, little m and capital M, this should be initialized to be n, right? So then this the same. So now let's iterate. So for the iterate, we change a little bit. So let me just delete that. Then what we're going to do is, so n is the length, right? So let me n equals the length of nums. And then we're going to do is for I in range, so iterate from the last index n-1, and then we're ending at index 0, right? So then, so let me right, in a parallel. So we can call this or just not if nums I is less than little m, or nums I is larger than capital M. In other words, outer bound. So we can update outer indices to be I, right? So for this version, you need to interpret the outer index and the M index and the capital M index accordingly, right? So, and then we are going to set M thin to be false and the capital M thin to be false. This is one check. Another check is if nums I equals little m. So in this case, so we update the M index to be I, and we check M thin to be true, right? Another check is nums I equals capital M. So then we're going to set M index to be I and M thin to be true, right? Again, so after this check, so we're going to see if M thin and capital M also thin. So then we're going to update the result. However, this update formula is slightly different, right? It's because the outer indices is in the red, so we're going to outer index minus so the max of this M index and M index. So notice here, right? So in the front previous vision, so what we are going to do is that we use the mean of this indices M IDX and capital M IDX minus the outer, right? Because the outer index is to the left, so because we iterate from left to right. Now here we have outer index in the right, and then we're ready to minus the max of these two. So notice that so the meaning of this max or min corresponding to the very left, so here corresponding to the very right, but smaller than the index. So here is corresponding to the very left, but it's smaller, right? Smaller than the outer index. But here, but this is still larger than the current index. So with that done, so we are ready to do the return. So now, actually, we can do a check again. Yeah, it passes the example. So generic case. Yeah. So with that said, I guess that's about it for this problem. So in this video, we analyzed a solution based on the sliding window technique. So we shared two formats of solution. So iterating from the beginning to the end, or from the end to the beginning, to demonstrate the flexibility once we digested the main idea. So with that said, I guess that's it for this problem. Thank you.